I'd like to introduce Dr. Jose Soto. He is a family medicine physician, and he's going to talk about other issues related issues on astronaut training. So it's a good segue from the prior session. So welcome, Dr. Soto.
Thank you. Thank you so much. Well, thank you so much. I think the previous presentation was great and actually intimately linked with this presentation. I'm Jose Antonio Soto. I'm a family physician. I also teach medical students at Ross University School of Medicine. And on December 2016, I have the idea to develop and execute an expedition to Mount Everest Base Camp. The idea was to explore the effects of altitude in individuals, and I came up with this project that actually was very interesting. The idea was arriving to this area here. This is the original Everest Base Camp, and that was Mount Muche. But what is high altitude? That was the first question I had. What is high altitude? How high it is when we say high altitude? Well, there are different levels of high altitude. Like we start with high altitude in 1,500 meters, and I say the metric numbers because that's the most commonly used in Nepal. But it's about 5,000 feet, and that's the altitude of Denver, Colorado. Also Kathmandu, the capital of Nepal. I arrived to Kathmandu, and then after a couple of days of acclimatization, I was transferred to Lukla. Lukla is at 2,800 meters, and it's the most risky or more dangerous airport in the world. It's in a slope. So imagine, landing in something like this. It's a 12-degree angle airport. Very risky at 2,800 meters. You meet your Sherpa, your guides, your porters, and from there you start walking, which is trekking, and it's trekking up, so it's climbing also, to higher altitude. You go to Phakdin, which is at 2,600 meters, your first night there, and then to Nanche Bazar the following day, which is at 3,500 meters. That's very high altitude. You start feeling the symptoms of acute mountain sickness in a very mild degree. Shortness of breath, chest pain sometimes, you feel tired, you feel fatigue sometimes, and then little by little you start adjusting, and then you start walking from a small village to a small village day by day until you get to Gorachep. Gorachep is at 5,100 meters or 200 meters, 5,200 meters approximately. And then that's the original base camp. That's where the base camp was originally located. From there, you take a couple of days or 1 day of acclimatization, and then I tried Kalapatar. I climbed to 5,643 meters. That's extreme altitude. Let me tell you, it's really, really tiring. You feel exhausted, you feel short of breath, you feel tired, but the views are out of this world. Actually, I did this. It's an observational study of a 53-year-old man. I couldn't find a partner, a friend to go with. It's difficult to convince someone to go to Everest Base Camp. But it was 7 days of recording data, ascending, and hour after hour. It's never been done in the medical field. I was recording the data hour after hour, sitting down in the middle of the trek, and then start writing the temperature, the distance, the altitude, the heart rate, the pulse oximetry readings, so the oxygenation, the saturation of oxygen in the blood, and it was intense. It was from 98 in Miami Beach, where I live, to 71% in Mount Kalapatar. Is all of that in 7 days. You feel really exhausted, tired. Also, I expend during the effort about 23,000 calories, and that's about 4,000 calories per day of effort. This is only data on the ascent. And the average heart rate was 140 beats per minute, but the highest heart rate was 189, and that was actually at the level of Phakdin, was at the beginning of the trek. Then I measured the average, what was the heart rate in between this town, and then from this town to this town, and that's the maximal heart rate average, and the maximal heart rate was about 158 per minute. So this data here, this number, 140 beats per minute is actually the average of the total heart rates measured, and that was consistent with the average heart rate on training when I was training for this event. And this graphic is very simple. The higher you go in altitude, the lowest is the oxygenation. Was up to 71%, here 74, the next one will be 71. And that was 5,640 meters of altitude. It was very, very clear. And as you see, is irregular. The body starts to try to adapt and cope with different altitudes, but is actually responding very well. Thankfully, the Sherpa was laughing at me, and they were saying, oh, look, he's from the beach, and look at here, he's not getting sick. So I had to treat someone with cerebral edema in the trek. I injected them with dexamethasone, was a person, a man from 26-year-old. He passed me really fast in the ascent, and I go like, wow, look at what 25-year-old people can do. But he was going too fast. And then he developed cerebral edema, headaches, vomiting on a cliff, so I injected him, sent him down. He was doing fine. He was doing great after. This is important data. It's the pulse oximetry, and the pulse, the oximetry, and the altitude, 3 elements linked. So this is the highest heart rate I got in the ascent. And as you see the trend of the heart rate, actually, the acceleration is going down. So the heart rate remains high, but the acceleration, the higher you go in altitude, the lower is the acceleration of the heart. So the heart still goes fast, but you expect to go faster because you're shorter of oxygen. Actually, apparently the heart can't. When you are here at 134 beats per minute, it's the same feeling that when you are here at 189 at a different altitude. So because of the altitude, the heart cannot pump. Apparently, for some reason not clear, it doesn't pump that fast. The oxygenation also was another element here, is the oxygenation was coming down consistently. Let me try this later, yeah. The oxygenation is coming down also consistently the higher you go in altitude. So this is the most, this is all concurrent with the literature. And then you get to this area, it's beautiful. You got the beautiful Mount Everest, Mount Shola. This is the Peak Nukshib up here. That one here is Lhotse, beautiful. You have the Khumbu icefall. This is the tent city, the area where the tent city is placed every year. And I'm taking the picture from Mount Kalapatar at about 5,600 meters. It's amazing what you see. But then when I arrive here, I say, this is another planet. This is rock, dust, ice, and you feel short of breath. You have a lot of layers of clothing on top of you. So I had the idea this might be a good training for astronauts. Why? Because of the things of space. When you travel to Mars, you're going to experience a lot of symptoms. And this is a long list of symptoms, of psychological symptoms that I developed during the studies. You feel tired and fear. You have fear all the time. You have fear of failure. What if I cannot do this? What a shame. You're going to be spending all this money, all this training, all these years. And fear of being injured, fear of dying. There's no 911 in Everest. So you're facing your own mortality right there. You get notified that someone died recently, and was a French gentleman, young man, who passed. Unfortunately, he fell and he died. He separated himself from the guys, and it was a very sad story. But you're hearing that, and you go like, well, let me not be too close to the edge, we move this side. Nobody knows until you are in altitude exposed if you're going to be able to make it. There's no medical test that you can predict that you're going to do the high altitude or not. Also, you have feels of frostbites, and you feel homesick. You have mood swings. You see that frequently in other members of the crew, the people that are with you. People get sometimes agitated easily, irritable, all because of the lack of oxygen. Also anxiety. And all these things, are being reported also in astronauts. In the trip to Mars, I'm sure many of the astronauts, or some of them, are going to experience some of these symptoms. That was not Mars, by the way. The picture is in Hawaii. It's in Mauna Kea. It's a lava field. This is Mauna Kea. But the similarity is striking sometimes with the red planet. And then these are the clinical symptoms that we have. Essentially, shortness of breath, a lot of shortness of breath, palpitation, tachycardia, the heart goes really fast. You feel fatigue, weakness, pain in all the joints and the muscles. That's constant. Also nasal discharge. You lose your appetite frequently. So the Sherpas that are used to these environmental changes, environmental extreme environment, they also help you to guide. They guide you continuously. And also constipation, borborism is you feel the intestine goes like goes too fast, abdominal distension, you feel it. Frequency fluid, and this very interesting data here. Scotomas, you see like lights and streaks sometimes due to the intense radiation, and you see fluid redistribution. So facial edema, you get the lips swollen, the eyes sometimes get swollen around the eyes, you see that. Those are symptoms also reported in astronauts. The story of Polyakov, Valery Polyakov, is immense. He stayed 438 days in space, actually 437 plus 18 hours. So I call it 438 days in space. And he has 2 environmental adaptations that were extreme. First time when he went to space. So he was all immediately floating in the space, and he felt overwhelmed with the tasks he has to do. He needed assistance from Earth for that during about 2-3 weeks on space. And then when he came back to Earth, after this enormous record, he also needed assistance. He became also, he had changes in mood and problems with attention. So all of this is data, this being published. So not only in space, adaptation, this when we go to Mars is gonna be double. Twice in the space for a long time, and twice arrival to different planets. Once Mars is gonna be rocky, it's gonna be a different gravitational field, and then when they come back to Earth, it's gonna be more gravity. So all of these problems might be very extreme. In other parts of this, and something else that is really important is the dust. The components of the dust in Mars are gonna be aggressive. The presence of perchlorates and chloromethane might be very irritating for the astronauts, especially remembering the Apollo missions where the moon dust was actually very, very aggressive with the astronauts, and they complain all the time about this. This is not Mars, this is Everest Base Camp Trail. And also we have a lot of dust here. The dust in Everest Base Camp Trail is very irritating. There is something called the Kumbu cough, and that's a cough developed by the climbers, and it's very, very irritating, bronchitis. It's not clear what is the particular reason for that cough, but we associate that with the dust. So there's a lot of similarities between mountaineering and Martian exploration. First of all is the passion for exploring, the passion for discovering, the unpredictable weather, because we don't know until this day what is the weather pattern exactly in Mars and how to predict events in Mars. The explorers in altitude have to be dealing with that all the time. You need to know what the temperature is outside, what the prognosis is, what to wear, and you need to both need to use a specific design wear. So you need to use special suits, number of layers. The teamwork is also very important. Rationing of supplies is really critical in the exploration in both. And overall, the psychological and physical adaptability to these remote environments is actually very important. The most important tool to take is a pulse oximeter, and these are the records of the pulse oximetry. The average pulse oximetry was 87, and the median pulse was 84%. This is percentage of oxygen in the blood. Normally, we should have here about 97%. So we went down there, or I went down there up to 71%, and that's actually doing well. That's a well done thing, no problem. You feel short of breath, but this is, we see someone in the ER with this, we need to call pulmonary intensive care unit. This patient might need intubation. So we might need telemedicine there in Mars. Look at the similarity between Mars, the rover photography, and Mauna Kea in Hawaii. And this is Mauna Loa, where the high seas exploration, space exploration program is located at. These are pictures of the rocks I picked up in the expedition to Everest. And look at these rocks are in Mount Kalapatar. This is the top of Mount Kalapatar. And the rocks are very similar to the ones in Mars. This one, I thought it was a meteorite. I brought a magnet with me, an Earth magnet, and I found this black rock, actually this one here, and then this one. And I checked and it was magnet positive. I said, wow, I found a meteorite. I sent it to the Meteoritical Society in Boston, and they responded to me, it's not a meteorite. They sent me a piece to prove that they're not playing games. But it was actually an iron or possibly an iron foundry. So I reported to the Department of Geology and Mines in Nepal, because this could represent something important. Mountains of rocks of iron in Nepal might be actually something important for the Sherpas. And we know that prolonged missions to Mars or prolonged missions in space, microgravity is associated with body wasting. This body wasting, we've seen it. This is a simple Google search, for astronauts returning to Earth, and everybody is brought in arms or brought by stretchers out of the capsules in Kazakhstan. There will be nobody waiting for us in Mars after 6 months of traveling. So this is really important. Not only the muscles will change in the muscles, not only the muscles will change in power, in shape, but also there will be changes, microscopic changes in the muscles. The human body physically change in the trip to space. Even the muscle fibers that are thin, they're strong, that are big muscle fibers, they turn into fine, thin muscle fibers, fast twitch they call them, and this is only sometimes after 6 weeks. So there are physical changes in the body causing severe deterioration. We need to create countermeasures for that. Also mineral loss. Normal bone with osteoporosis, look at the big difference. The size of the trabecles, the bone trabecles are bigger here, the spaces. And that is the area where we are gonna have more of this bone osteoporosis, is the lumbar spine and the hip. Actually areas responsible for carrying weight. So when the astronauts arrive to Mars, they're gonna be weaker, they might have bone mineral loss, they will have to put new spacesuits, they will have to carry heavy backpacks, and a fracture of the hip or a fracture of the spine, it's going to be actually something critical in the space exploration. So something to keep in mind. What happens when you climb mountains is that in altitude is you start losing muscle too. This is another similarity, muscle loss in altitude. So we don't know how this happened. It's not clear. It's apparently connected with lack of oxygen. But especially also this is something you see expansion of the lungs, and you see new areas of the lungs being expanded and being recruited for more breathing. So that happens, it's called alveoli recruitment. So when you go to high altitude, new areas of the lungs start breathing. And this is an experiment I did in 2006, and with purified ocean water. There is salty water in Mars that might have also medical uses. Numerous layers, even materials that we use for climbing mountains, these are very, very similar to what astronauts use, and those are all materials used in spacesuits. Mountaineering can help you to get used to that too. And then the proposition is very interesting. Try to have a Mars analog in high altitude. That would be something good. If we can use the knowledge of Sherpas, this is Lakpa Jelu Sherpa, that they know about environmental extreme changes, the environmental challenges, how to face, and they'd say, you sit down, drink water. Doctor, you have to take your notes now. And I go, oh, wow, this man had got the hint immediately of how to keep with high altitude. And this is at the original Everest base camp in Gorachep. We should go from high seas or high altitude to very high altitude. This is Aconcagua in Argentina. We can create something similar here. That would be very good to test the crew, to see how they perform in altitude, to see how the team bonding is. 2 words about the exoskeleton might be very useful in a space mission for rescue operations used by the rescuers to access an astronaut that might be injured in a mountain or in a cave. Also to carry an astronaut, the model that is the fixed model or the rigid model might help you to carry up to 200 pounds. I spoke yesterday to the Lockheed Martin group. The recovery and rehabilitation, and also to be used in chronically injured astronauts is actually one of the 2 very important uses for the exoskeleton in the space mission. Definitely something to do. So the conclusion is that the altitude climbing is a controlled simulation of the after landing physical condition and after post-traveling effects of microgravity. It's ideal for physiological and psychological preparation and evaluation of the team to see how they interact, what happened with this team once they are exposed to tiring, to fatigue, to isolation, how they're gonna have their relationships, how it's gonna be their strength and the vulnerabilities of the team. Also to test the new gear or the gear they're going to use in Mars, the interaction with robots and robotics during the expedition, and also to develop protocols for safety, and this will lead definitely to a faster adaptation and less accidents in Mars, and a lot better results. And this will be the model of a side mountain for about 10 days, then with deployment and settlement of the crew, acclimatization at the beginning, and then ascending to the about 5,000 meters of altitude above the sea level, while they conduct research activity, a rescue simulation, do the gear performance evaluation, and then descending and extraction. I think that if this is a composite picture of a picture from Mars Curiosity and a climber in Kalapatar. I think the success for Roald Amundsen conquering the South Pole was the simulation of the traversing the northern fields of ice fields in Europe. And I think if the way to the stars is hard for the astronauts, for the mountaineers is actually very, very literally harder because they literally walk to the stars. Thank you. Yes.
Did you, or what medicine did you take to prevent high altitude pulmonary edema and cerebral edema?
Why I took a very good question. What medicines I took to the high altitude? Well, I took acetazolamide and dexamethasone. Acetazolamide, I used the 250 milligram tablets. Dexamethasone was, I took it in tablets of 10 milligrams, or 4 milligrams actually, and the injectable form, the 10 milligrams. Yeah, those are the main, but you have to take a lot of creams, yeah, you have to take antibiotics. I took medication for anti-inflammatories, very important. I tried Benadryl to get some sleep. It worked very nicely, no tiring, yeah.
So would space explorers also need to take that medication?
Oh, if the space explorers, if they are gonna use it here in Earth, yes. In space, I think they're gonna be on a suit. The suit will have oxygen, so the oxygen level would be like in Earth.
All right, so that would be a difference between your experience and their experience.
That is correct, yeah. The similarity would be the exhaustion and the muscle.
Exhaustion, but not the oxygen.
Not the oxygen level, no. The oxygen level will help probably to simulate the fatigue because of the muscle loss in the space. Yeah, go ahead, ma'am. Definitely genetics. Genetics is involved in this because it can happen that people that are good runners at sea level might underperform in altitude. That's why it's important to see what part of the crew might not be tolerant to high altitude, and that might be a criteria probably to disengage them from that activity. Not necessarily say they won't qualify for astronauts. They can be excellent astronauts.
Dr. Soto, my wife is an internal medicine specialist in San Francisco. She graduated from the University of Buenos Aires Medical School and began her medical career in Argentina.
Nice.
Before coming here, make a long story short, she's been with me in all these Mars Society things for years, and she's always and she's an avid hiker and does these extreme climbs as high as 15,000 feet. But she's always commenting that there's not enough emphasis on space medicine. What happens to the humans when you put them in that very exotic environment? And my compliments for your efforts and this presentation.
Oh, thank you so much. I think it will be a great opportunity for astronauts to train, in high altitude. We can see the bonding of the team, the interactions, and also evaluate them physically and physiologically and psychological.
The gentleman who you treated for some high altitude illness, did he take his medicine?
Actually, it was a young man, 26-year-old from Destin, Florida. He actually passed me in the morning, early in the morning. He passed me really fast, and I go like, wow, look at the young guy. And then I found him later in altitude, about 4,000 meters. He was throwing up in the cliff, and he told me the day before he was with shortness of breath, and in that moment he was having headaches, and the vomiting from headaches is because of the brain edema, swelling of the brain.
Did he take medicine prophylactically?
No, he didn't. No, he didn't. I gave him a shot, and then I sent him down. 3 days after, they told me he was doing great. So I counseled him that, you're gonna feel well, but don't come back because, you may think you call a helicopter, and there's no 911. They sometimes come, sometimes they take 3 days to come. It's a different set of rules there.
We've got to wrap up now.
Yeah. Go ahead.
There was a recent book entitled Evolving Ourselves. They pointed out that humans people go over the death as Morris there is that there's one change in the crocodile hemoglobin, which could be done to humans, which would increase the capacity to withstand lower oxygen density. So there's a lot of opportunities there to evolve.
Absolutely. I've been in Ethiopia. I lived there for 8 months doing voluntary work in Ethiopia, and I've been in the Tibet area in Nepal. Even with the same hemoglobin A, hemoglobin F, the same set of hemoglobin by hemoglobin electrophoresis is actually the affinity of the hemoglobin by the oxygen, and that's very particular. Some people in this room will be very avid capturing oxygen, some others won't. So sometimes you see older people doing well in altitude, you see younger people not doing well, you see women beating you up right and left, and you know your macho part goes like down because they do better. Many times they pass you and they run a mile from you. You know, it's really, it goes from individual to individual. But that's a good point of yours, yeah. Thank you.
Very much.